I'm very happy to be here. I've had so many exciting conversations over the last day that I'm almost lost my voice. So this may be the last thing I say thing during this conference. My last comments during this conference will be this talk. The experiment I'm going to tell you about today is done jointly with Professor Jun Yi at Jilla. So I'm going to tell you about the electron. The electron is a friendly guy. He's very small, he's very cute, he has a charge, he has a mass. Like me, he's very happy to wish happy birthday to Dan. And let's see, what else can we tell you about him? He spins, and therefore he has a magnetic moment. And that, in principle, is about all there is to know about the electron. But maybe there's more to it. For instance, perhaps it has an electric dipole moment. In addition to its monopole charge, maybe there's a little positive near the north, a little negative near the south, then it would have an electric dipole moment. Every time anyone's tried to measure this number, yes? Oh, I don't really. It's a good point. Maybe this is Ms. Electron. Signora Electron. If you have an offset, anytime anyone's measured this, they measure 0, but perhaps it's not 0, as we'll talk about. If you see if you have an electric dipole moment on a charged particle, you can think of that simply as an offset between the center of mass and the center of charge, which means you can really refer to the electric dipole moment just in units of some, how big that distance is. In the world I live in, I like to think of electric fields and magnetic fields as having the same units, and similarly with electric dipole moments and magnetic dipole moments, they're just basically in units of distance times some charge. Okay, so let's try and understand, what might the electric dipole moment be, maybe just on dimensional grounds. The easiest way to create sort of a dimensionful number for an electric dipole moment would say, well, how about the transition dipole moment in a hydrogen atom? That's about the Bohr, about 1 Bohr. And so that, of course, is a relatively large number. We could ask, well, suppose it's comparable to the magnetic dipole moment of an electron, which is just the Bohr times a fine structure constant, but that also is way too large. We can add 1 more power of the fine structure constant and get something called the classical radius of the electron. This is just if you take 1 unit of charge and press it into a tiny little ball until the charge energy is equal to the rest mass of the electron. That's the classical radius of the electron, and also that's still something which is way too large. Now, if you think about the electric dipole moment as being an offset between a center of charge and the center of mass, that sounds like structure. So we can, well, how would you measure the structure of a particle? Traditionally, in particle physics, you take 2 particles and smash them together, and the best you can do is at the Large Hadron Collider, you smash 2 particles together with about 5 TeV. The characteristic scale there is 10 to the minus 19 e-centimeters, quite a bit smaller, but still too big compared to the experimental limit. The current experimental limit, if we take this classical radius of the electron and expand it until it's the size of the entire world, then the current experimental limit would correspond to the diameter of a virus. So it's an almost amazingly small number, a very good limit set. And we know that the electric dipole moment of the electron, if it exists, is smaller than that. We'd like to go at Jilla and at several other groups around the world, we'd like to do an additional 2 orders or perhaps 3 orders of magnitude better than that. So why would we ever want to do this? Why would we want to come up with a limit which is now 16 orders of magnitude, which would be 16 orders of magnitude smaller than sort of a natural length scale for an electron? And the reason has to do with a search for new physics for particles beyond the standard model. To get this 16 orders of magnitude, you could think of, this is sort of a classic Feynman diagram for a dipole moment. There's a static electric field which the electron would interact with. But before it interacts, maybe it will convert from an electron to, a neutrino, and meanwhile emit a photino. Or new physics typically starts with small s's because of supersymmetry. And this is, of course, not really a calculation, but people sort of say, well, the typical scale of this would be some sort of mixing angle for violating CP, and then a mass ratio squared. So if this particle has a mass ratio which is presumably quite a bit larger than the electron, then that would suppress the electric dipole moment. So if we can set a limit of 10 to the minus 16 in these natural units, And we assume that this mixing angle is some natural mixing angle, not 0, not 1, but somewhere in between. Then sort of a typical scale of particles that we can at least get a hint of their existence might be 2000 GeV. And we should compare this with the recent discovery of the Higgs particle at 100 GeV. So precision measurements in atomic and molecular precision measurements in this particularly narrowly specified way can really compete with the LHC, with big accelerators in trying to discover new particles. So this experiment is done with lots of help. My senior grad student Huan Chen Lo and senior postdoc Gongquen Ni, Jun Yi, and I have been working on this for a long time. We have a lot of help from John Bone and Chris Green and other local theory or local theorists, and we have non-local theorists in Russia who help us. We talk a lot with Bob Field at MIT, who teaches us things that I didn't know before about molecular physics. So how do you measure an electron's electric dipole moment? It's probably easier to ask how you ask a magnetic dipole moment. It's almost the same thing. If you have a magnetic field and an electron with a magnetic moment, you shine radio waves, you flip it over, you find the frequency that gives you the maximum probability of flipping over, and that frequency is just the magnetic moment times the magnetic field. Now, if you also had an electric dipole moment, then if you apply an electron, you'll get a very small shift in that frequency. If you apply an electric field in the opposite direction, you'll see a shift in the opposite direction. You take the difference between those two frequencies, the magnetic field drops out, and you're just left with the electric dipole moment times the electric field. So conceptually, a very, very simple experiment. If you want to do a good experiment, you need to apply a really large electric field. You need to have a really long coherence time, so you have narrow resonance lines. And you need to have a reasonably large count rate, so you can split the lines. So a sort of figure of merit is, what is the effective electric field applied to the electron? What's your coherence time? And what's the number of spin flips that you can observe in some finite time, say the lifetime of a graduate student, some sort of experimental unit of time like that. Big problem is if you take an electron, you apply an electric field to it, especially a big electric field to it, the electron's gone. So there was a great idea from Pat Sanders at Oxford, which says we take the electron, we stick it to a heavy nucleus, and now you have an atom with an unpaired spin, and you get this relativistic enhancement of the dipole moment, plus it's neutral so it doesn't go anywhere. The gold standard for these experiments was Eugene Cummins, who for many, many years was sort of the front runner, always had a somewhat better measurement than everyone else. Finally, he gracefully retired. Dan would approve. Dan says, eventually you have to retire so that other people can have a chance. So this was good. And now we're all trying to catch up with him. Our approach is we want to, unfortunately, there's a limit in the lab to what kind of electric field you can apply to an atom. You take two metal plates and you apply a big electric field between them, and you can get up to about 100 kilovolts per centimeter. You go any bigger than that, you just get sparks. So nature's way of applying a very large electric field to an atom is in a molecule. So think sodium chloride. The sodium is very positive, the chlorine is very negative. The chlorine atom is doubtless experiencing a very large field. In our case, we use hafnium or thorium and fluorine, which is a very negative atom, to apply a large electric field. A relatively small field in the lab, say 10 volts per centimeter, stretches out the molecule, and then the molecule applies the really large electric field to the electrons. You can get an enhancement of 9 orders of magnitude. It's like an electric field multiplier. You apply 10 volts in the lab, you get 10 to the 10 volts on the electrons. Then, of course, we want to have a long coherence time, so work in an ion trap. And this way, I'm going back to my childhood at MIT when I was trapping molecules in ion traps. We all somehow want to go back to when we were children, and this is my way of doing it. Basically, in order to compete with the Eugene Cummins, you somehow have to do better than the classic atomic beam experiment he did. And so all these other groups are, one way or another, trying to compete with him, either with larger electric fields or larger coherence time or larger count rate. A group in London, led by Ed Hines, is currently made a measurement which is slightly better than Eugene Cummins. These other groups are trying their different things. Our particular advantage is to have a very large electric field and a very long coherence time. What this means, if you look at our resonance line, the width of our resonance line expressed in units of, expressed in electric dipole moment units, our line is very, very narrow. We anticipate if we can split our line even by a part in 100, then we'll have a significant new measurement. So this means that many, many systematic errors have to do with misunderstandings of your line shape, but splitting a line by 1% is child's play. So we hope this will give us an advantage, which we'll need because our count rate is correspondingly very small. We're the only group doing this in an ion trap where counts tend to come in at several clicks per second as opposed to thousands of measurements per second. Okay, so we put our molecule in the ion trap. We prepare the spins up. We try to flip over the spins. We see if they flip. We find the frequency that maximizes this flipping, and then we do the experiment now with the molecule inverted, take the difference in those two frequencies, and we're all done. Doesn't sound very hard, but I've been working on it. I've been working on it since Dan was 70. Really, getting to be a while now, almost a decade. We come in, to make these, we come in with an ablation pulse. We vaporize our metal, be it hafnium or thorium. We do some chemistry with some neutral gas and some sulfur hexafluoride. We make the fluorine version of our atom. They come into our trap. We turn on the trap, and then we do our spectroscopy there. And by the standards of modern ion traps, we have sort of a low-performance ions trap. Instead of the ions being confined within a micron or two, the characteristic scale is 15 centimeters. It's a Powell trap. What we call our radio frequency is only 30 kilohertz. It's a big, slow, fat, lazy trap, which is good for precision metrology. You don't want to apply really large fields. So how can you do precision spectroscopy? I mean, the whole point of an ion trap is the electric fields are very inhomogeneous. You're trying to push the ions into the middle. It sounds like a very hostile environment to do precision metrology. And we borrow an idea from Dave DeMille, who says that, well, if molecules that have 1 unit of angular momentum projected along the intermolecular axis have this wonderful feature, which is that each state comes in a parity doublet, a positive parity state and a negative parity state. They're quite close together in energy, which means you apply a relatively small electric field and you can stretch the molecules up and down. And those two states, the transition and this transition is essentially at zero frequency. You apply a little bit of a magnetic field because physicists don't like to measure zero frequencies. We like to measure away from DC. Those two transitions should be entirely degenerate. I mean, these frequencies should be exactly the same, independent of the applied electric field and magnetic field. But if there is a little bit of electric dipole moment of electron, the transitions will be slightly different. So we take the difference of those two frequencies, the magnetic field drops out, the laboratory electric field drops out. All that's left is the electron's electric dipole moment times this internal field of the molecule. So even so, it's not completely straightforward to apply an electric field to an ion in a trap, because the whole point of ion traps is the ion wants to go to the place where the field is zero. If there's a field there, the ion would go somewhere else. So we decided to use eventually a heavy ion storage ring. Here we are in Switzerland, and if you think of the heavy ions in there going around very, very fast, there's a relativistic effect, which means there's always an electric field on the ion pointing inward. So I was inspired by that and went to our university president and said, we could have something just like that in Boulder. It would go under the stadium, it would be a tourist attraction. The president said no. I said, well, okay, I understand, sir, maybe I'm being a little ambitious. What if we make a smaller one, just like that, only a kilometer across? No. Well, we could make it really small. No. Well, we could just, outside of Jilla, we have this lawn. We could put one there, only 5 meters in diameter, and people could play Frisbee on top. No. So we decided to make a really small storage ring, and here it is in scale. I don't know if you can see it. There's a picture of it. Here's the Jilla heavy ion storage ring. There's Huan Chen Lo, Kang Quen Ni, and Jun Yi, and the other students. So if you look very carefully, well, I can't see it yet. We better go a little closer. Oh, I still can't see it. Oh, there it is, to scale. Now, to be fair, this graduate student is my largest graduate student of all time. But even so, this is still a very small thing, something less than a millimeter in diameter. And it's not really a storage ring. It's just a rotating electric field. The electric field rotates slowly enough that the ion can track the direction of the quantization axis, tracks very nicely, but it's going rapidly enough that the ion doesn't have time to go very far before the electric field changes direction. So it's sort of confined inertially. And then we have supplementary electric fields, much like the focusing fields in an ion in a storage ring, but in our case we call it an ion trap. If you think about it, a storage ring is kind of like a really large ion trap. Okay, so I'm short on time, so I won't discuss this, but John Bone spent a lot of time thinking about what the best kind of molecule to use is. It turns out that molecules that have this particular symmetry, the triplet delta 1 is really good. They have very small magnetic moments and typically very large internal electric fields. He and his student evaluated very many different molecules and told us the ones you want to use are either hafnium fluoride plus or thorium fluoride plus, or if you want to do a neutral version of the experiment, as the guys at Harvard and Yale are doing, they were suggesting thorium oxide. And they all have very large effective fields. This corresponds to 100 gigavolts per centimeter, 10 to the 10 volts per centimeter, sorry, 10 to the 11 volts per centimeter, very, very large electric fields. Okay, so the problem is we don't do laser cooling. The atoms come out of this expansion, the molecules come out of this expansion, they're at 5 Kelvin, 10 Kelvin, because we have lots of vibrational structure, lots of rotational, fine structure, isotope. This corresponds to an occupation of maybe only 1 ion per every 300 is in the state we want. So 1 ion contributes to the science signal. The other 300 ions are just space charge, decoherence causing background. That's a problem. So to solve that problem, we decided to rethink ion loading. Instead of just making our ions in this hot ablation and trapping them, we actually get rid of the ions. We let the neutral atom molecules come into our trap, and then we ionize them in a very gentle way, in a very specific way. We actually use some ideas that date back to, well, people like Dan Kleppner, which is we use Rydberg. Of course, in this case, it's not a Rydberg atom, it's a Rydberg molecule. We shine a laser to an intermediate state, and then a second laser in a different color to a Rydberg state of the hafnium fluoride atom, the neutral atom. Let me draw, this is more schematic. Here's the hafnium fluoride neutral molecule. We excite to a quasi-bound state. If we can think of this as a very loosely bound electron, the Rydberg level is 14 or 15, I think. And the ionic core is vibrating. After a little while, the vibrational energy gets transferred to the electron flies away, and we're left with a neutral hafnium fluoride molecule. But the advantage is that this is a bound state, or at least a quasi-bound state. There's narrow transitions, and we can do this transition to a particular value of the angular momentum, a particular vibrational level. We even have isotope sensitivity, which means that we can pick out the line in here that we want that corresponds to a very low angular momentum state here. This process, which is called shake-off ionization, is very gentle. And what's left is an ion with no vibration, and in many cases, a single J level and even a well-defined M level. So we can get just about, we start with 1,000 ions, we can get 30% of them into a single magnetic sublevel. So now we've gone from 1 part in 300 to 1 part in 3. Okay. Unfortunately, when we make the ions, they're in the wrong states, so we have to do a coherent transfer. We come up with 1 photon, down with another photon, wind up in the triplet delta state. If I expand that triplet delta state and look at the magnetic sublevels, by picking the polarization of that laser and the energy of that laser, we can pick whichever of these states we want to start in. And so here's the data for that. It turns out I didn't tell you about the hyperfine levels. So there's actually, the fluorine atom has a spin, so there's a hyperfine structure there. And as we sweep this laser frequency, we can see coherent transfer into 1 and then the other state. And now if we turn on the electric field, there's actually 6 separate Stark states. And here at various different electric fields, we can resolve all those Stark levels. Here this is plotted against the applied electric field. The red lines are, the red dots are the data. We can extract the molecular frame dipole moment of the molecule, the hyperfine splitting, and so on. And that's all working very well. So the final big problem for us is how do we read out the spin state? Basically, we want to drive a radio frequency transition from here to here. It's a very low transition. I call it radio frequency, but typically we're operating at about 50 hertz. You can't really see absorption of a single 50 hertz photon. So we somehow need to amplify this up. We tried doing laser-induced fluorescence, where we would come up with circularly polarized light and capture the photon, but the sensitivity was horrible. So now we call something we call REMP-D. It's kind of like REMP-E, except instead of ionization, it's dissociation. We come up to an intermediate state in the molecule, and then we blast it with a very strong ultraviolet photon, and we found a repulsive curve up here. We break the hafnium fluoride plus into hafnium plus and fluorine. So we put in one circular polarization or the other circular polarization, which tells us which of these two M levels it's in. Contingent upon absorbing that photon, we can absorb the second photon. It falls apart. We've got little detectors here. The hafnium fluoride plus fluorine ion, when it falls apart, it has a different charge to mass ratio. When we dump it out of the trap and count it here, there's the hafnium fluoride plus, and that's what the hafnium plus looks like. So basically, we just count how many hafnium ions arrive. That tells us how many radio frequency transitions we make, and it's kind of a triply resonant kind of spectroscopy, but eventually we can do this. Okay, so we do some photodissociation spectroscopy, and the difference between doing REMP-D, resonantly enhanced multi-photon dissociation, compared to laser-induced fluorescence was about a factor of 30 in counts per second, so that was really good. So we need to know where all these electronic states are. As an atomic physicist, I feel that I should just be able to look in a book and find out where all the transitions are. There was this lovely lady, Charlotte Moore, who figured these all things out. But unfortunately, that's not true for molecules. You take any two molecules and stick them together, there's about 10,000 of them. Papers have been written by only about 5% of them. So most diatomic molecules, simple molecules again, no one's ever studied. It's very frustrating. We spent several years doing the survey spectroscopy. We had a big oven, and we had this enormous discharge. It was very 1950s feeling. And we did spectroscopy on it. Gradually, we're able to look at these rotational levels. What we found is that scanning this laser, okay, scanning the laser was not particularly 1950s. That was a little bit more modern. It was a very, very slow thing to do. It would take us, days and days to collect this small amount of data. So Jun Yi got involved. Jun Yi is a frequency comb guru. And he was always looking for new fun things to do with frequency combs. And what he did is he has a frequency comb laser with one frequency tooth every 3 gigahertz. We couple that into a cavity, which is a natural multiple of that frequency. So every single frequency comb goes into a different cavity mode. It passes through here because there's a cavity where we get enhancement. Then we disperse the frequency comb onto a camera. And we see, let's see, many, many teeth. So each of these little dots here corresponds to a single spectroscopy measurement. So in a single moment, on our CCD camera, we can detect thousands of spectroscopy experiments all at once. So we take many images. You can see here where the image is dark, that corresponds to a dispersion down. Where the image is light, there's a dispersion up. We take many images like this and we intersperse them. And eventually we get these very complicated looking spectra, but we can collect hundreds of wave meters of, hundreds of wave numbers of data in just an afternoon. So in a relatively small amount of time, we were finally able to do the survey spectroscopy of this molecule. It's really complicated looking, and that's because there's lots of fine structure, there's lots of vibrational levels, everything, isotopes, it's all interspersed. It took us a long time to understand what all those lines mean. But eventually we had good models for these different electronic states. We learned about the vibrational spacings, the rotational spacings, all these things we need to know. And so we have some atlas of 10,000 lines in hafnium fluoride, and we can predict the positions of another 20,000 more. And we're just now starting to do this for thorium fluoride plus, which is an even better molecule, although it's a little radioactive, and there's a lot more paperwork associated with working with it. So where are we right now? We've been able to put the atoms into a single Stark level, and we're just now beginning to drive these transitions from here to here. Because of the hyperfine structure, the transition we want to make is a 3-photon transition, 1, 2, 3. It's a little bit difficult to do a 3-photon transition, but we actually kind of borrowed another idea kind of indirectly from Dan. Just when I was getting to MIT, he was doing these beautiful experiments in Rydberg atoms where the magnetic fields and electric fields would change. I can't do justice to this, but basically you could just adiabatically ramp these Rydberg atoms into circularly polarized states and things like maximally circular orbits. It was beautiful things, it made a big impression on me at the time. So we want to go from here to here to here to here. The sort of the brute force way to do this would be to do this with 3 somewhat off-resonant photons, but we're already a little bit hyperextended, and the thought of doing all that was kind of daunting. So what we decided instead was to take advantage of the fact that these M levels are defined in a rotating electric field. Now, rotation couples, an infinitesimal rotation couples 2 adjacent states that differ with delta M equal 1. In principle, it doesn't couple delta M equal 3, but you could have a higher order process. You could go from here to here to here to here, basically third order in perturbation theory, which sounds like it would be very weak because the rotation rate is very slow compared to this Stark splitting. But we apply a relatively small magnetic bias, which means that these 2 states are almost on resonance. This is a positive magnetic bias field. There's a negative magnetic bias field. A 0 magnetic field, they're exactly on resonance, except that this rotation via a third order perturbation process couples those 2 states. So if I just look at the energy of those 2 states as a function of the magnetic bias field, with a big bias field, it's, you know, the states are, the good states are M equal minus 3/2 or M equal 3/2. As I go to a vanishing bias field, the rotation via this third order process mixes those 2 states. And I get an avoided crossing, where the splitting and the avoided crossing is driven by this third order term, this third order rotation term. So the way we do our spectroscopy now is we apply a magnetic bias field, we do some optical depletion, so we have a state in the pure M equal minus 3/2 state. Then we quickly turn the bias field off, and the ions are projected into this state. They rotate in this projection, and then we quickly turn the bias field back on, and now we have the ions in a superposition, a coherent superposition of these 2 states. We wait a little bit, we do it again. That looks a little bit like 2 Ramsey pulses, doesn't it? And then, again, we measure which polarization it is. So this idea finally worked about a week ago. So I've been doing this experiment for almost 10 years, and we've seen Ramsey fringes on the science transition for the first time only a week ago. I have data which I brought, and my student sent me some more recently, but they have embargoed it. They've told me that I'm not allowed to show this to you because there are things that they're still checking. And I've decided that I will respect their wishes. But you should see it. It's very nice fringe. I don't know why they're so nervous about it. It's the frequency is about 50 hertz. And don't tell them I told you this, but it tells us that the magnetic G factor of this molecule is very small. Something, because it's a triplet delta 1 molecule, in the Hund's case A limit, the magnetic moment would be alpha over pi or something very, very small like that. The G factor would be something like alpha over pi. It's a little bit larger than that because it's a heavy molecule, but still compared to a barrel, ordinarily, an electron should have a G factor of 1. G factor is down by a factor of about 200 or something, which makes us relatively insensitive to magnetic field, which is one of our largest systematics. Okay, so I realize we need to get off to lunch. Statistical sensitivity, we think in about a day of data, we could probably do about a factor of 30 better than the current limit, which means if we're willing to integrate for a while, we could do two orders of magnitude better than the current limit. Systematic errors, we know how to chop the magnetic field and electric field rotation direction. I mean, a key thing about this experiment is that once you've applied an electric field which is large enough to fully polarize the molecule, the science signal is independent of the applied electric field, and independent of the applied magnetic field, and independent of the rate of rotation. All the systematic errors we can think of should scale with those things. We have enough signal to noise that we can afford to do the experiment many different times at different electric and magnetic fields. So we have ways of detecting systematic errors, powerful ways of detecting systematic errors. We haven't thought of, an improvement of a factor of 10. We certainly have not been able to think of any important systematic at that level. Beyond that, we'll have to rely on these powerful techniques for smoking out the unforeseen systematic errors. So we feel like we've really got to try this, and we're a lot closer now than we were a year ago. Dan, happy birthday. I learned a lot from you. Many of the things I talked about, I first experienced in your graduate AMO class at MIT. These notions of avoided crossings and Landau-Zener and all these sorts of things. The idea that it's sort of reasonable to think about dipole moments, both magnetic and electric, in units of length, that's sort of it's actually a useful idea. So thanks for your attention.
It would be laboring the obvious to say that this is a tremendously exciting experiment. This is one of the most exciting things going on in our field today, and I think everyone wishes you luck. And I can't help but think, of course, of Norman Ramsey. His picture was up at the beginning of this.
Yes.
And he started this field.
Yes.
And he spent his whole life searching for the EDM of the neutron, and the experiments got better and better. They never found it, and he never lost his enthusiasm for that. And so I think built into this experiment is this wonderful tradition, this wonderful spirit of pushing on and hoping for the best.
I agree.
Eric, in that vein, I have very strong memories of Norman showing his famous view graph of plotting the theory of where people would find the EDM of the neutron, and then his experiment, and how no matter where he did it, there'd be another theory the next day, next year, that would be just below where he was. Is there something similar going on here?
Yeah. Theory is a very nebulous thing, and especially, I mean, the main motivation for this is these supersymmetry and various extensions to the supersymmetry, but there's lots of varieties of it. They have adjustable parameters. Realistically, if we see 0, it'll be very hard to actually definitively murder supersymmetry, which is what I really want to do. But the only thing that supersymmetry has going for it is that it's beautiful, it's pretty. There's no data supporting it. So if you can load down supersymmetry with a lot of unattractive baggage, like, oh, it has to be fine-tuned to suppress, you make it less fashionable. My goal in the end is not to kill supersymmetry, but to sort of push it off the slate of fashion. I want it to sort of be like the Paris Hilton of theory or something. We don't talk about it so much anymore. So that's really the hope.
So you mentioned that when you think about having an electric dipole moment, that it sounds like structure. If you found an electric dipole moment, would that imply that the electron has structure, i.e. non-zero size? And would that have any implications for G-2, for example?
I don't think so. I mean, okay. The fact that G-2 is not 0, that already in some sense says the electron has structure. What it means is that around the electron, it polarizes this cloud of stuff. It's the same thing here. It's just sort of saying that around the electron, the bare electron, there's this polarized cloud of stuff. This particular polarized cloud of stuff violates CP invariance. But I don't think it's any more structure in this measurement than there is in the G-2.
More questions? Okay, so let's thank Professor Cornell again.